Well, we've looked at numbers now, we've looked at the language of mathematics, and now we're going to examine the powers that be, exponents. And the first thing we'll look at are integer exponents. So let's see what we've got here. Integer exponents. Well, I'm going to motivate this with an example first. And let's imagine that we'd like to multiply the following. 2 times 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 2. You got that? Well, you know, whew, that's a lot of 2's to multiply. It's awkward to write down, and I'd like to have some kind of shorthand for that. So what I will do is use this shorthand. I will say I'm going to take 2 and I want to multiply it. If you count there are 10 of them. I want to multiply it 10 times, so I'll write 2 to the 10th. That is nice and compact, as opposed to multiplying out like this. And just for those of you that would like to know what 2 to the 10th is, that burning question, 1024. Happens to be the same thing as 1 kilobyte, if you're into computers. But the important thing here is this shorthand. This shorthand is what I'm going to be describing right now. So let's make this official. We have a number. We're multiplying it a certain number of times, and I'm putting the number of times up here. And we're going to want to expand that, so let's go ahead and get an actual definition down. Definition. And this will be for any real number. So any real number A. All right. Here's what I'm going to define. A times dot 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 up to A. Suppose we multiply together n of those. N, and these are equal, so I'll even mention that. N equal factors. What we'll do is we'll write this notation, A to the nth power. Now let me explain what we have here. This shorthand notation needs explanation. This number A is usually referred to as the base. It is the number you are multiplying out. The number n, well, we can call that several things. It's going to be for us right now an integer exponent. That's one of the words that's used. Exponent. It's also referred to as a power. That explains the title that I used for this section. It's called a power. It's also, for those of you that know word processing, it's a superscript. Right? It's a number that is above the line of the base. Now, remember these are integers. These n's here are going to be 0 plus or minus 1 plus or minus 2 dot 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 out to infinity. Now right now some of those don't make much sense. It's certainly clear that if I want to multiply A 6 times, I can write A to the 6th, that's the way you say it, and that makes sense. But it's not clear what 0 would mean or what negative numbers would mean. So we'll have to get to that in a moment. But there we have a definition. So let's go ahead and see how this works. We need to make one other minor definition because I mentioned A to the 0 power, and we will simply define that for convenience to be 1. Now that will make all of our other operations, as you'll see, work out. This, however, only works for A not equal to 0. So to put it another way, the form 0 to the 0 is undefined. And just as division by 0 was undefined, that 1 over 0 form we looked at before, this is also undefined. Now I'm not going to show you any more than that. You can sort of see why this wouldn't be something that you could easily define, because the 0 to any power sort of takes this number towards 0. On the other hand, if something to the 0 is 1, that 0 above would tend to make this 1, and there's a conflict there, which is the reason that this remains undefined. Now here's an example just to show you how this works. 2 to the 0 power is 1. Right? There you go. 2 to the 0 power is 1. You can take negative numbers. Negative 105 to the 0 power is 1, etc. Any real number taken to the 0 power except 0 is going to be 1. Now just as a minor note here, because there may be someone out there that's thinking of this, you have to be a little careful. In context this won't be a problem. But don't confuse 0 power with degrees. Remember when you write something like 45 degrees, if you've looked at angles, there's that little O up there. It looks like a 0 power, but that's not what it is. So in case that occurred to you, don't make that confusion. All right, well that's 0. That was a special case I wanted to get out of the way. Let's get back to numbers, to powers that make a little more sense to us, at least on the surface. Let's start out with this. A to the 1. Well, that would be A, because you're multiplying A by itself once. So that makes sense. Now, how would we say that? Well, we could say, like I said, A to the 1, or we could say A to the first power. There's one way to say that. Let me point out right now that to the is the English way of saying raise it up. Put it as a superscript. Okay, let's go on. A squared. Whoops, I just said something I need to explain. I should say A to the 2 power. A to the 2 power is simply A times A. There are two A's there. And so we can say A to the, we'll say second, how about that? Second power. But as you heard me say just a moment ago, we also say A squared. Now why would we say A squared? Well, this actually is related to a square. I'll tell you why. Because if you take a square of side A and you figure its area is this A to the second power. So to say A squared seems natural, and that's where this comes from. Now, most of the exponents we see will not have their own special names, like A squared. But A squared does, and there's one more, the very next one, A cubed. So A to the third power is A times A times A. We could say A to the third power, if we like. We also say A cubed. And again, this has a geometric meaning. So why would we say that? We say that because if you have a cube of sides A, and A, all three sides are A, what is the volume of that cube? The volume is A cubed, or A to the 3 power. So that's the reason cubed is used here, because that's exactly the kind of figure this comes from. Now, A squared and A cubed are the only ones that have these special names, these sort of historical names. All the rest of them, when we have A to the n power, which remember is A times A times A n times, so there are n factors here, we usually just say A to the nth power, whatever n is. So for 4 we'd say A to the 4th power, for 5 we say A to the 5th power, etc. They don't have special names. All right, as we proceed through here, I'm going to give you little warnings and tips on how to deal with exponents. So first now, let me give you a warning. This is something that we can talk about right now, so let's go ahead and do this. This will have bearing later too. This will recur. Warning. And what's the warning about? It's about even powers and negative numbers. And numbers, of course, I mean, again, real numbers. So this is a warning about even powers and negative numbers. And here's why. Let me just show you one example so you'll be sensitized to this. Take minus 2, a negative number, raise it to the 4th power. Now what does that mean? That means minus 2 times minus 2 times minus 2 times minus 2. Well, minus times a minus, you may recall, is a positive number. The same thing with the second pair. So this is 2 times 2, which is 4, times 2 is 8, times 2 is 16. So minus 2 quantity to the 4th power is 16. All right. This is not equal to, this, by the way, is the not equal sign. As symbols turn up in the course, I'll introduce them to you. That's the not equal sign. This is not equal to minus 2 to the 4th written that way. Notice there are no parentheses here. So the grouping that is intended here, this is minus quantity 2 to the 4th. When the minus is out front, it is assumed to go over the entire expression. Up here, the minus is only for the 2 because I have parentheses around that. Now you see what happens here. Minus 2 to the fourth, 2 to the fourth is 16, so this is minus 16. And that certainly is not equal to 16. So be very careful. I'll put this down here. Placement of this minus sign and grouping matters. Okay, grouping and the placement of the minus sign. My matters is running off the screen here a little bit, but you heard what I said. You want to be very careful how you read these. And the more examples we see throughout the course, the more you'll become sensitized to this. And you'll have a chance later to do some of your own examples. All right, let's summarize where we are at this point, because I did digress into the warning. So far, we've seen what? We've seen a to the n defined for powers what? N equals 0, 1, 2, 3, etc. But I said in this section we were going to talk about integer exponents, and integers include -1, -2, -3. So, but what about negative integers? What could that possibly mean? What could things like a to the -1, a to the -2, a to the -3 mean? Now, we don't want them to have an arbitrary meaning. They have to be connected to our number system somehow. So we ask ourselves, what could they mean? Well, I'm going to leave you with that question now and just let you wonder about it for a little bit. We'll come back to this. But you might ask yourself, what could that possibly mean? Powers that are numbers like this, it's easy to see, and the 0 we've defined. But what are these going to be? So I'll leave that for you to ponder. Go back to my list, and the next topic under integer exponents will be operations with integer exponents. Now that we know what they are, let's go ahead and do some operations with integer exponents. All right. First, let me show you an example. First, we'll do an example to kind of set the scene here. Imagine you have 3 to the 4th. Well, we know what that means now. That means 3 multiplied by itself 4 times. And we wanted to multiply that by 3 to the 7th, say, which is 3 multiplied by itself 7 times. Well, if you write this out, 3 times 3 times 3 times 3, that's 3 to the 4th, multiplied by 3 times 3 times 3 times 3 times 3 times 3 times 3, 7 of them. Now, you know from your long experience with numbers like this in your elementary school years that the parentheses don't matter. We can just consider this a long string of 3's. How many 3's are there? There are 11 factors. 4 plus 7. So that only makes sense that 3 to the 4th times 3 to the 7th ought to be 3 to however many 3's there are. 11 of them. So it looks like we might have a rule. This suggests the following. A rule generated from this idea. Now I'm doing this rule first because it's a very important rule, and we'll get whatever we want from this. So I'll even say that. This is an important rule. And based on what we just saw, the rule goes like this. If you have a to the m power times a to the n power, then based on our previous example, it's clear that what you do, since you have m a's multiplied and n a's multiplied, you simply add the exponents. So suddenly we have a rule, a to the m plus n. See, these rules don't come out of nowhere. They actually are based on examples. I'm not going to prove this in general. I think you see how this works from the previous example. Now, this only works, of course, let me make that point at least, they must have the same base. If you were multiplying 2 different numbers to powers, this wouldn't work. But if it's the same number to powers, you simply add the powers, because that's how many times you're multiplying a. So for example, 5 to the 11th times 5 to the 9th is 5 to the 20th. How did I get 20? I took 11 and 9 and added. I noticed that the bases were the same, and so I've just followed the rule. And so you can try out examples like this on your own. All right, so now we have a simple rule, and let me ask a natural question at this point. Question. Suppose we consider the following situation. Suppose we consider 5 to the 10th times 5 to the box, something, don't know what, equals 1. Suppose we look at that. Now the question is, what could this be? What number might we put up there that would make this expression true? Well, let's see. By the rule, on the previous page, when you multiply two powers of the same base, you add the powers. So I can rewrite this as 5 to the 10 plus box. That's equal to, well, I'm going to rewrite 1 also. I'll rewrite 1 as 5 to the 0, because remember, 5 to the 0 is 1. So 5 to the 10 plus box equals 5 to the 0. Well, if the two bases are the same, that means these powers up here better be the same. So, equating powers, what do we end up with? 10 plus box equals 0. Well, that's an easy equation. Let's solve for box. Subtract 10 from both sides of it. So that ends up moving the 10 over, and I'll move it over here. We end up with box equals minus 10. Ah, now I'm getting an idea here. So what does this mean if box is minus 10? Let me rewrite what I have up here with the box filled in. Thus, I have that 5 to the 10th times 5 to the minus 10th equals 1. Apparently, I've discovered something. But wait a minute. But we already know something. We already know that 5 to the 10th times 1 over 5 to the 10th equals 1. Because any number times its reciprocal is equal to 1. Well, if 5 to the 10th times 5 to the minus 10th is 1, and 5 to the 10th times 1 over 5 to the 10th is 1, then this and this must be the same thing. Hence, we decide that 5 to the minus 10th is 1 over 5 to the 10th. Aha! Now we have something that we can define, because this makes sense with our number system and what we've been doing. So, definition. A to the minus n will be defined to be 1 over a to the n, based on our example with 5 a moment ago. Now this is only going to work. It's got a little bit of a restriction. A can't be 0. That makes sense because we don't want to divide by 0. We already know we can't do that. And the only n's I'm talking about here are n equals 0, 1, 2, 3, etc. Because these we've already defined powers for. And so now we have them all defined for negative numbers. So let me say something about what we've just done here. This definition, first of all, it's a new use of the symbol bar. Okay? That symbol is now used in a different way. It is not subtraction, which is exemplified perhaps by 13 minus 5. It is also not negation, as in, say, minus 7. Negation, you might remember, is going left on the real line. This new symbol's usage is neither one of these. If you wanted to think about it, I suppose you could say what it is it says, rewrite this as the reciprocal, 1 over a to the n. So the minus simply says, rewrite me as a reciprocal. But I'm not going to say that. We're just going to memorize this rule as it stands because we know it makes sense now. And let's look at a couple of examples. 13 to the minus 4 power. What does that mean? That's 1 over 13 to the 4. I don't know what 13 to the 4 is, and I don't care right now. I just want to illustrate what the negative power means. Here's another example. The number here does not have to be positive. Suppose I took minus 6 to the minus 3 power. Now these are different uses of the minus sign. This is 1 over minus 6 to the 3 power. So the minus here indicated reciprocal. It's just a plain 3 down here now. Well, with these two examples, I begin to see something else that I want to talk about. So I'll do a little by the way here. Notice the following. Or notice again, because I think we talked about this briefly in another example earlier. If you take minus 1 times minus 1, you get 1. Now that's what? That's minus 1 squared, an even number. Also, if you took minus 1 cubed, minus 1 times minus 1 times minus 1, what do you get? Well, two of them, as you know from the previous case, equal 1, times minus 1 equals minus 1, and so on. Well, this certainly suggests a pattern. In fact, it's a pattern worth writing down. So I will write it down in the form of a mathematical fact, and let's call it a handy lemma. So I get to use that word, lemma. A handy lemma. Here's the handy lemma. Minus 1 to the odd n power will always be minus 1. And minus 1 to the even n power will always be 1. And what n's am I talking about? Let's be clear. Where n is 0, plus or minus 1, we've got them both defined now, plus or minus 2 all the way out to infinity. In other words, all of z. So, this turns out to be very handy. If you take minus 1 to any odd power, you get minus 1. If you take minus 1 to any even power, it is always 1. So, when you're faced with what's minus 1 to the 101 power, you don't have to do any work. 101 is an odd number, so this is going to be minus 1, and so on. Now this turns out to be a surprisingly useful fact. There's not much to it, it seems, but you'll see it again and again. So let's continue on with our rules of exponents here. We write down other rules because we haven't exhausted them yet. And just so we have it on this page, let me recall the one rule that we do have. We have a to the m times a to the n equals a to the m plus n. Now we have that rule. And this now works for all of the integers we've seen. So let's go ahead and see what else we can write down. And these, you have to understand what these rules are. These are common sense rules. If you practice with integers, integer exponents at all, you'll see that these things work out. For example, what would a to the m all taken to the n power be? Now you can just write the rule down, but let me show you why it's true. Let's put an intermediate step in here before I actually write out what this is equal to. The intermediate step says, well, what does this mean? This means the thing inside, which happens to be a to the m, is multiplied by itself n times. So this is a to the m times a to the m times dot 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 times a to the m, and how many of them are there? There are n factors here. Well, how many m's do you have? N m's. So how many numbers in all do you have? You have a to the m times n. And there's your rule. A to the m, all taken to the nth power, ends up multiplying these two numbers. But you see why that's true now. So even if you were to forget this, you could try it with a couple of numbers and see what the rule has to be. That's the way you want to remember these rules. You don't want to just commit these to memory without understanding of what's happening in the middle. All right, let's take another one. Suppose you have two numbers, a times b, a pair, multiplied together and then taken to the nth power. Well, before I write down the other end, let me put in the middle. What does this mean? It means ab, the quantity, is taken to the nth power, multiplied by itself, ab, 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 n times, n factors. Well, from what you know about numbers, multiplication can be reordered any way you like. So I have how many a's here? Well, I have n of these ab's, so I have n a's. I also have n b's. So if I reorder them differently, this is a to the n times b to the n. And there I have a rule which says the n power distributes over the two inside factors. However, you now see why that's true. So it shouldn't be a mystery that this works. And again, if you know why things work, then if you happen to slip up, you can reconstruct them. That's how people really remember most of mathematics. All right, let's do a couple more here. What if you have different powers, same base, different powers, a to the m over a to the n, a division? What would this be? Well, here's a way to think about this. This is a to the m times 1 over a to the n. So that's just rewriting the bottom part as a single fraction. That's what that means. So this is a to the m times, well, 1 over a to the n, we define that to be a to the minus n. And now we have a situation where we have one base to a power times the same base to a power. What are we supposed to do? We're supposed to add the powers. That was the very first rule we saw. So this is a to the m minus n. So this first one becomes a to the m minus n. However, there's another way to think about this. So let me show you that other way. Or, instead of rewriting it a to the m times 1 over a to the n, let me go ahead and move the a to the m down. Write this 1 over a to the minus m times 1 over a to the n. So this first one is rewritten in a different way. Remember now, the minus says go to the other side. It just flip over, do a reciprocal. So that's why a to the m is 1 over a to the minus m. Well, now I have these two on the bottom multiplied together. When you multiply them together, you add the powers, as we saw in the first rule. So this is now a to the n minus m. So it depends on what you want here. Do you want to have a fraction that has a 1 on the top and a number on the bottom, or do you just want a number on the top? And it'll depend on what you're looking for in a given case. Okay, here's one more. What if you had a fraction, a over b to the n? Now we did this a moment ago with a times b. Now we're doing the division. Well, again, this is a over b times a over b, dot, 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 times a over b. There are n factors. So how many a's are there on top? A to the n. How many b's on the bottom? B to the n. And there you have yet another rule to add to your collection. So you will have time in a little bit to practice all of these rules. But let me give you one more warning. This is a warning. And remember what we saw before? I'll even write it up here. Before we saw that if you had minus 2 to the 4th, that was minus 16 because you really thought about it as broken down into minus times the quantity 2 to the 4th. All right, here's my warning. Be careful. Be careful what object, what mathematical object that is, your exponents, or your powers, if you like that word, your powers or exponents apply to. Now that really repeats this idea. But I want to go ahead and show you a few more examples because there are some things that you can run into, some difficulties you could run into if you don't watch it. So let me show you a couple of standard kinds of errors that can be made. Look at a times b cubed. Now, I warn you that this is not the same thing as ab quantity cubed. This 3 power only goes with the b. If you want it to go with the a and the b, you have to put parentheses. Because ab cubed, as you know from our previous set of rules, is a cubed, b cubed. And that certainly is not the same thing as a times b cubed. So there is one thing that you want to be careful about. Let me show you a similar example. Same problem really, but looks a little different. A times b to the minus 1. Well, if you follow my advice here, the same advice works here. This minus 1 only applies to the b. So this is not ab quantity to the minus 1. But you can check that more directly. A times b to the minus 1 is a over b. B to the minus 1 is 1 over b. ab to the minus 1 is 1 over ab. You see, these two are not at all the same. So it does matter how you write things, what you group things as. So keep that in mind. Let me show you a couple more fallacious arguments here. A cubed times a to the fourth. Now you know from our rule, we've said it a couple of times, what you're supposed to do. You're supposed to add the powers. This is definitely not equal to a cubed to the fourth power. Because as you know from the rule, this is a to the seventh. 3 plus 4 is 7. That's how many a's are multiplied. And this one is a cubed taken to the fourth. This, of course, is a to the 12th. And these, of course, are not at all alike. So once you understand how these work, it becomes harder to make mistakes. Let me show you just one more here. A to the minus 1 plus b to the minus 1. This is not the same thing as a plus b to the minus 1. We've never said anything about exponents distributing over a sum. And this is a perfect example why that's not true. A to the minus 1 plus b to the minus 1 is equal to 1 over a plus 1 over b. That's what the minus 1 means. On this side, this is minus 1 applied to the whole thing. So this is 1 over a plus b. Now you know from your knowledge of fractions that these two fractions are not the same. And if you have any doubts, put in a couple of simple numbers just to remind yourself. But they're not at all the same. All right, well, we've seen a lot of operations on these integers now. Now that I've given you some warning, what I'd like to do is show you how some exercises are worked out involving integer exponents, because you'll have a chance to practice with these. The exercises all look the same way. They all start off with something like the word simplify, and then there'll be an expression, maybe like this: x to the fifth, y to the minus 2, all over x cubed y. And for the sake of argument, in case anyone wonders, we'll just assume, so we don't have any division by 0, that x is not 0 and y is not 0. Okay, so there's no division by 0 problem. Now our goal here is to simplify this. Why does anyone want to do this in algebra at this point? Well, to give you some practice in dealing with exponents. Many of the operations and the kind of functions we see later will involve exponents, and you need to simplify them because, frankly, this is too hard to look at. There's too much complication there. I can't tell what's going on. It's important to us to have things simple. Now, I'm going to write down one solution. Why did I write one? Well, because this is not the only way to do this. The art of simplification is simply to get this to be simple. Everybody does it a little differently. I'll show you some standard practice, and you might want to imitate that. But when you get to be more familiar with this, you'll choose other paths. So let me rewrite that here. X to the fifth, y to the minus 2, over x cubed y. First rule of thumb, and I will mention this as a tip at the end. First rule of thumb is get rid of those negative powers. Rewrite them so that they're positive powers. Now what does that mean? That means y to the minus 2 must be rewritten as 1 over y squared. So basically that's going to move that downward. So let me do that first. X to the fifth now is left alone. On the bottom I have x cubed y times y squared. So this has been moved downward. Well, now you can see what's to be done next, and we could do two jobs at once. Y times y squared, there's 3 y's multiplied, that's y cubed. And then we had a rule that said x to the fifth over x cubed. This is x to the 5 minus 3. And that makes sense when you think about it. You have x times x times x up here, times x times x. 3 of those over x cubed equals the number 1. So this is the rule, but that was the reason. And so you end up finally with, let's slide it in here, x squared over y cubed. Now that is much, much better than the original. Here we have a single thing on the top and the bottom and no negative powers. So the dreaded negative powers have disappeared. So that's a simple example. Let's do another one, because you need to see more of these and do a lot of these on your own. This is not what this course is about. This is simply, you might think of it as finger exercises in music. You have to get used to this. So I'll do enough of these to give you some practice. X to the minus 2 minus y to the minus 2 over x to the minus 1 plus y to the minus 1. And again, so that we don't have division by 0, I will assume that x is not 0 and y is not 0. All right. Here I go. One solution. My pathway to simplification. First of all, I'm going to rewrite it. I have 4 negative powers. Don't like that at all. I'm going to rewrite that, get rid of them right away. So what do I end up when I rewrite that? End up with? I have 1 over x squared minus 1 over y squared. Now that is on top. And on the bottom I have 1 over x plus 1 over y. So it looks like I've made things worse. Well, only temporarily. I have no more negative exponents, so I consider that a bonus. All right. Now what I need to do on the top and the bottom, because I want to apply some of the rules we have for fractions, I'm going to combine the top into a single fraction, combine the bottom into a single fraction. How do I do that? Well, I have to get the same denominator for both of the things on the top and for both of the things on the bottom. The technique for that is, this is the top now and this is the bottom, 1 over x squared. Well, if I want my denominator to be x squared times y squared, x squared needs a y squared down here. Well, I can't change things, so I multiply 1 over x squared by y squared over y squared. That's multiplying by 1, so I haven't changed anything. Minus, do the same trick here. 1 over y squared, I will multiply top and bottom by x squared over x squared. Again, that's 1, no change. But now you notice the denominators are both x squared times y squared. Same thing down here. 1 over x, I want x times y to be my denominator, so I'll multiply by y over y to make this have the correct denominator. And then 1 over y I will multiply by x over x. So I have the correct denominator here. So now I'm all set to write the top and the bottom as a single fraction each. So let me do that. I will bring this back so you'll be able to see what I did. This is equals. Continue from the previous page. You want to have a string of equal signs now. Now what do I have? I have the fraction on top, which will have as its denominator x squared y squared, and the top will be y squared minus x squared. On the bottom, the denominator we got was xy, and on the top it'll be y plus x. Now since you don't have the previous sheet in front of you, let me bring it back. There's what I had. So you see x squared y squared is the top's denominator, and what's on the top of that? Y squared minus x squared. And on the bottom, xy is the denominator for both, and what's on the top? Y plus x. And that's exactly what I have written down here. Well, now I have a single fraction over a single fraction. I know how to deal with that. What was the rule? Let's see. I copy the top. So I have y squared minus x squared over x squared y squared. Just copy it. And what's on the bottom? What am I supposed to do with this? I'm supposed to flip over and multiply. In other words, write that as a reciprocal. So let me do that. Multiply and flip it over, so it's now xy over y plus x. So I'm on my way to getting a simpler expression. Almost there. Now I'm going to do something that you probably don't expect if you don't remember this. Equals. I had two things. I'm going to make them into a single fraction. Let me remind you now what I had. That's what I had. Since these are multiplied, to multiply fractions, remember I multiply the top, I multiply the bottom. So the bottom becomes x squared times y plus x. The top becomes y squared minus x squared times xy. Now, this happens to be an expression we'll talk about later, but that can be rewritten. This can be what's called factored. I can write this expression as the product of two other expressions. We'll talk about that later, but let me go ahead and do it here. I can rewrite this as y minus x times y plus x. So this becomes factored just like this. And then still I have the xy. And on the bottom I have the x squared y squared and the y plus x. And now I'm ready to finish. Y plus x, y plus x. Y plus x over y plus x is 1. So I don't have to write these anymore. Also, I have x and y here, and I can pull out an x and a y here. xy over xy is 1. What's left? Y minus x from here, and then 1x and 1y from here, and I'm done. This is much simpler. Let me remind you of what the original one looked like. The original one looked like this, and rewritten looked like this. We've improved things considerably. We have y minus x over xy. Very simple and straightforward. And when you do further calculations with this, you'll be much happier to have it this way. So, let me give you some tips now, and then we'll take a pause, and you'll be able to practice this on your own. So here are some tips. Some of them I've already said, but let's get them written down here. 1, let's be careful with groupings. If you have any doubt, put in parentheses where you think there should be parentheses. It's better to have them in there than not to have them in there. Secondly, I recommend that you keep the division form, the quotient form, where the top is directly over the bottom in a vertical manner. Keep that form, not another form that you will see in textbooks that looks like that. The reason you don't want to do this is because this is for textbooks, or you say this is also useful for calculators and computers and computer systems. That's the way you very often have to enter things. Why? Because the computers and the calculators like to have everything on a single line. But when you work it by hand, this is by far superior. It keeps you mentally aware of what is happening and makes the operations easy to remember. So do things this way. Finally, as another tip, always rewrite negative exponents immediately, or negative powers immediately. Okay, that's very important. As you saw, it makes things easier to work with. Let me give you one more example of that before I leave you. These are the tips that you really want to jot down in your notes and keep aware of. These are rules of thumb. These are the result of experience. And one more thing. 1 over x cubed is more useful in the practice of writing down calculations than x to the minus 3. Similarly, x to the 5th, now you'll believe this one I know, is more useful than 1 over x to the minus 5th. Now these are equivalent, as are the first two. But if you keep things without negative powers, it's going to be easier for you to follow the rules and to simplify your expressions. So on that note, let's take a pause, and you can go ahead and try some of these on your own. Now that I hope you've had some experience with integer exponents, we're going to talk about another topic. And at first, it may seem like it's not related. The topic is square roots. And I've got semicolon there, a pair of equal factors. Now, what do roots have to do with exponents? It's a good question, and that's why I've set aside square roots first, and then we'll look at other kinds of roots later. So let's first talk about square roots to lead us into this. All right. Actually, there are both of those words need explanation, square and roots. We haven't talked about roots at all. Here's what we say. We say a to the second power, remember we say a squared, is a, and sometimes we write the word perfect, I'll put it in parentheses here, is a perfect square. And what we say, as I said, is we say a squared. Now, why again was that? Remember, that's because if you have a square of side A, then the area of that squared, the area, is equal to A times A squared. All right. Once we say that, and we say also the following. We say that A, the number here that is taken to the second power, the base, the thing being squared, we say that A is its square root. Now, the use of the word root is an older piece of terminology that has lingered on. It is simply the base, if you like, or the number that is squared in this case. So that's where square root comes from. So let me say it another way. So, A is the square root of A squared because, I'm repeating myself, but I want to get this clear, because A times A equals A squared. That's what a root does. And notice that these are a pair of equal factors. Factors, you remember, are things which are multiplied. All right. So square, this is a pair of equal factors. So now we're going to generalize. And how am I going to generalize? Well, I'm going to not start out with a number that I write as A squared. I'm just going to call it X. And then look for the number that would multiply by itself to give me that X. So this will be in the form of a theorem. I'll call it a fact just for short, but it is a theorem. Fact. And here is the generalization I mentioned. For any x greater than or equal to 0, so any real number that is either 0 or positive, there exists a positive number, okay, a positive number whose square is x. Meaning, I'm going to write this out so you know what I'm talking about. Meaning, x is equal to this thing squared. Okay? This theorem says that if you give me any number which is 0 or positive, then I can find another number whose square will equal x. This thing here, this thing that will go in the box, this is called the principal square root of x. It is the positive number. Positive is what principal means here. Positive number such that when you square it, you get x. All right? And it's denoted as follows. It's denoted by this square root symbol. This number is the number which, when squared and put into that box, equals x. Now, this is a funny notation. In the part on the language of mathematics, we talked about this notation and that it might have resulted from a corruption of drawing the letter R here. You also note that I put a tail on the end. That's something that I will continue to do. But this is now the symbol for the number which, when squared, equals x. Let me write that out so you're clear on what I'm talking about. Meaning, by definition, if you take the square root of x and you square it, you get x. That's what the symbol means. Now, let me notice something else while we're here. Notice that if you take minus square root of x and you square it, you also get x. So that happens too. That's why the other one was called the principal square root. So let me summarize. The square root of x is the principal square root. Principal means positive here. All right? Positive. There may be other square roots. In this case, negative square root of x is the other square root. And this, of course, is negative. So the principal one is the positive one. The other one, which is called the negative square root. All right, let's look at some numerical examples. Example. What is the principal square root? Principal square root. Long time to write that out. Square root of 2. Well, the answer is, using the symbolism, square root of 2. Now, I can't do any better than that because square root of 2, as you know, is an irrational number. That is the symbol I'm going to use, and that's all I can say at this point. What is the principal square root of 9? Answer, 3. How do I know that? Because it's positive, and 3 times 3 is 9. What's the principal square root of 1? To start with some of the ending cases, the cases that are sort of on the edge. Answer, 1. 1 is its own square root, because 1 squared equals 1. What is the principal square root of 0? Answer, 0. Another number that's equal to its own square root, etc. Okay? Now, in general, finding a square root is simple as writing down the symbol. If you want to simplify this any further, it's going to depend on what the number is. If the number is 9, then the square root is 3. That's easy. If it's 2 and you get an irrational number, there's nothing you can do but write this down. If you were really interested in what this number was, you might get an approximation. And you can do this with calculators these days. But let me say the following. Square root finding. How's that for a phrase? Square root finding is just, here's another way to think about it, unmultiplying x. Unmultiplying x into 2 equal factors. And you can do that, as the theorem said, with any positive number or 0. And just to repeat myself here, by example, 2 is equal to the square root of 2 times the square root of 2. I have taken 2 and unmultiplied it, we'll later call that factoring, into 2 numbers which are the same, square root of 2. 9 is 3 times 3, etc. So that's what square root finding is. All right, now I started this section saying, what does square root have to do with exponents? This is a whole section on exponents. So let's pose a question here. Question. Could we write the admittedly strange symbol, because it's an older symbol, say symbol square root of x, as perhaps a power of x, or an exponent of x? Could we possibly do that? Well, if we could, this would be handy, because we have a lot of rules for powers, and if the same rules apply, then we'd be in good shape. Let's see. We have to make an argument. We have to come up with a reason for rewriting this as a power. So let's see if we can come up with one here. Let's see. Since the square root of x times the square root of x equals x, that's the definition of square root after all, what do we need? We need x to some power, unknown, x to the box, times the same thing, x to the box, equaling x. Okay? That's what we want to try and have happen. Well, we have a rule which says we can rewrite this. So by the rule, this is the same base, we can write this as x to the box plus box equals x. But box plus box is just like a number that's 2 times box, so this is x to the 2 times box equals x. And now this x over on the right, I'm going to write it as x to the 1 power to show that it has an exponent. Well, I have 2 bases that are equal. I want to equate the powers, or I can equate the powers. What do I have? I have 2 times box equals 1. Well, what does box have to be then? Divide both sides by 2. Box must equal 1/2. Aha! I think I have an idea now. We haven't had an exponent that was a fraction, but now it looks like this is the right thing to do. So let's see how this would apply. We then can write the square root of x equals x to the 1/2 power. See my little 1/2 there. So I've taken this rather odd square root symbol and written it in a power form. I'm familiar with powers. We've never had rational ones before, but now I have a meaning for rational. X to the 1/2 means the square root. So this on the left is an old notation. And this on the right is clearly it's a rational exponent. It's a power that is a rational number. And this is a new. And this is more useful. So let's put that down. This is a new, more useful notation. See, we don't invent new notations just to be different. We want to have something that makes things easier. So to summarize this, thus, if you take the square root of x squared, that is now the same as x to the 1/2 squared. And what was the rule for powers that were like this? X to something, all taken to another power, we multiplied the powers, right? So this is the x to the 2/2. But what's 2/2? 1. And what's x to the 1? X. So that just confirms that what we have here is a new notation that does the same thing as the square root symbol did. But with the new notation, we have all these rules that we can now follow. So let's go ahead and look at the next topic, which will generalize this. So let's go back to my list of topics. We looked at square roots, which is a pair of equal factors. And now let's go ahead and look at nth roots and rational exponents. The rational exponents we've already talked about. Now we're going to talk about nth roots. Those will not give a pair of equal factors. They will give n equal factors, as you will see in just a moment. So, nth roots and rational exponents. So this is the title of the section I am now looking at. And I'm going to generalize all of the work I just did with square roots. All right, let's recall what I just did with square roots. As I change the color on you here a bit. The square root of x. Now remember, square root is another word for the second root of x. The old notation was the square root symbol, and we have now got a new notation, x to the 1/2. Now let me point out one thing about the square root notation. You'll see in later notations that there is a number that appears there. The square root is the only one that doesn't have a number. You can imagine that there's a 2 there, if you like. That will make the rest of the notation look similar. So if square root of x is this, square being second, and we have 1/2, I ought to be able to guess that the cube root of x, now cube root is the third root, would be similar symbol except I put a 3 in there. So that would be cube root of x. And that you might expect is x to the 1/3. So based on what I did before, I'm now generalizing to the case where I have x written as a, not a pair, but a triple of 3 numbers that are the same. So let's go ahead and generalize these ideas that we've just developed. Generalize. because once you've seen it once, the rest of it is very similar. Definition. The principal, instead of square root, which is second root, I will say principal nth root. The principal nth root of a number, say a, is denoted the nth root of a. So it looks like the square root symbol with an n here. And the only symbol that you don't use a number for is square root. That's where the number would be 2, but it's not traditionally written there. So what does this mean? This means that a is equal, as I said earlier, a is equal to the product of n equal factors. So I am unmultiplying a into n factors, all of which are the nth root of a. So it's n equal factors, each called the nth root of a. So that is the fundamental idea here. Once again, I'm going to write down what this means so you have a good sense of it. Meaning, if you take the nth root of a and you take it to the nth power, you get a. Now, there's a little proviso here that we need to take into account. This will lead us to a later part of the course, so it's nice to put this in now. Provided that the following situation holds. When n is even, so we're talking about an even power here, or an even root. When n is an even number, a must be greater than or equal to 0. It must be positive or 0. And when n is odd, there is no such restriction. So even has this restriction, odd, a is any real number. So, why would there be such a restriction? Let me go ahead and tell you why on the next sheet here. The problem is the following. So, the form, which looks like this, square root of something to the something power, the form where this is even, this is an even n, and this is a negative number, any negative number whatsoever, that form is the one that I've just said is not defined in the real numbers. And that is the problem. It is not a real number. And why is it not a real number? Well, it'll turn out to be a complex number. So when I finish this section and we move on a bit, we'll talk about numbers again, and we'll come back to complex numbers. But such a situation, an even root of a negative number, leads to what are called complex numbers. They are not part of the real number system right now, but they will be later. So just bear with me and accept the fact that you can't take roots of that sort. So for example, of roots that you cannot take like that, you cannot take the square root of -1, which will turn out to be key for defining the set of complex numbers. You cannot take likewise the fourth root of -110, etc. Any negative number with an even root is not a real number. So if we get that out of our system, we're fine. Oh, and one small note while I'm here. Note, the nth root of 0 is equal to 0 for all n equal 1, 2, 3, 4, etc. Well, I guess we didn't really define a first root, so let's just say n equals 2 on up. Okay. So, let me recap what we've got. Remember, by definition, what is the nth root of a? You want to be very clear on this. It is the principal, that is to say the positive nth root of a. Now, for those of you that are interested, you know that square root, there were two different roots. There was the principal, which was the positive square root, and then the negative of that was the other square root. So a square root was, there are two square roots for a given number. You might expect that there are 3 cube roots, 4 fourth roots, and in general n nth roots. And if you did suspect that, you would be absolutely correct. Unfortunately, in most cases, the numbers are not real numbers. They are complex numbers. So, Although there are other roots, we'll have to put off discussing some of them. However, we can say the following. Fact. Again, fact is a theorem. Suppose you take the nth root of a to the n. Okay, so you have an nth power and you take the nth root. And let's assume that a is real, a real number of some kind. Then there are two possibilities here. If you take the nth root of a, you will get back a if n is odd. However, you will not, if n is even, the other case here, you will not get a back. And the problem is that if a is a negative number, for example, and you take it to an even power, a negative number like -2 taken to the 4th power, as you saw earlier in my example, is a +16. Then if we go ahead and take the 4th root of the +16, principal positive nth root, we get 4. But the original number under here was not, the nth root would be 2. The original number, however, was -2. I'll show you that in an example. But the end result is that you get the absolute value of a. You get a made positive if n is an even number. So let's look at two examples so that you'll see what it is that I just tried to explain. If I take the 5th root of -7 to the 5th power, I get back -7. Because when -7 is taken to an odd power, the negative sign is not lost. When I take the 5th root, the negative sign is not lost. However, in the case of the 8th root of -7 to the 8th, what happens? The process in here, -7 to the 8th, removes the negative sign. And then when I take the 8th root, the principal square root, the positive square root, I don't realize that there's a negative sign there. It's been lost. So I would just write down 7. So the way we've written that in our previous theorem is that the -7 is its absolute value when we take the 8th root of the 8th power of -7, and of course that's the 7 that I predicted it would be a moment ago. So that's one little kink you have to get used to. Never take an even power of a negative number, and if you do have a power underneath like this, the even powers will knock out the negatives. They disappear. Now there's an important special case. Back to square roots again. Important special case of that fact that I just mentioned. And that case is the following. If you take the square root of x squared, now that's the same theorem we just mentioned, it says this should be the absolute value of x. Well, look what that gives us. That gives us a very simple way to write the absolute value of x in terms of powers and roots. So this is sometimes handy. This, you can think of this as the box squared square root is the absolute value of box. So anything that you can put in there, the absolute value can be rewritten this way. So this is an alternative notation, or an alternate notation for the absolute value of x. And as an alternate notation, it sometimes has its uses. But let me write one more thing down here so I don't confuse anyone. Recall that this is not the same thing as taking the square root of x and squaring it. That is, by definition, equal to x. So the square root of x quantity squared is x. However, if you reverse the operations, the square root of x squared, you get the absolute value of x. And this is handy, so it's worth paying attention to. All right. We're talking about nth roots and rational exponents. We haven't talked about the rational exponents part of that, so let me go ahead and discuss that now. We had one example a moment ago when I talked about square roots in a previous bullet. I said square roots can be written as x to the 1/2 power. Well, now nth roots, you might expect, can be written as x to the 1 over n power. We now write the nth root of a as a to the 1 over n power. Just as before, we wrote the square root of a was equal to a to the 1/2. So this is a new notation. What does this mean? It's always good to keep writing down what this means. This means if you take the nth root of a, to the nth power. That, of course, is the same now as a to the 1 over n to the nth power. But that's a to the n over n. And just as before, we see that that's just a. So it will turn out that using this rational exponent notation is going to make things a lot easier. Let's go back to the list and see what's next. We've looked at square roots, we've looked at nth roots and rational exponents. Now finally, let's look at operations with rational exponents. So, operations with rational exponents. We did this before with integer exponents, and so a lot of this will be similar. The only difference is, instead of integers, we're now dealing with rational numbers. But the same kind of rules hold, thank goodness. And you know what else we can call this? We can also say this is operations with rational exponents and translations away from radicals. Radicals are those root expressions. Because that is another one of my rules of thumb that I'm going to give you, a tip. Do not, in most cases, leave problems in radical form. Write them as exponents that are rational. You'll find it to be much easier. So, here's the first of the rules. Suppose you have a to the m power, and you take the nth root of it. So m underneath, nth root. Well, what is that? That turns out to be the same thing, first of all, as reversing it. The nth root of a to the mth power. That will be written as a to the m over n. Because m is the power, 1 over n is the way we write roots. And if you want to confirm that, that's a to the 1 over n to the mth power also can be written as a to the m to the 1 over n power. Now, apart from those special cases we mentioned earlier, where you have negative numbers and even roots, this is a perfectly good rule, and you'll find it useful, and we'll try it in a few examples later. Let me show you a few more of these rules. They really will gel when you start doing examples. Suppose you'd have a, and you take the nth root of it, and then you take the mth root of that. Well, the inside part is a to the 1 over n, and then you're taking it to the 1 over m power. So the result is you have a to the 1 over mn. And that is the way you want to remember this. Immediately get away from the radical notation and get it into the exponential notation with rationals. It's much, much nicer. Let's do a couple more here just to complete the list. Suppose you take the nth root of ab. Rewriting that, that's ab to the 1 over n power. And then using the same rules we used before, you can rewrite this as a to the 1 over n times b to the 1 over n. And to do the quotient version, a over b. Now, of course, whenever I write a over b, I'm going to assume that the bottom's not 0, so we don't have nonsense. This can be written as, of course, a over b to the 1 over n, and then the top is a to the 1 over n over b to the 1 over n. Now, as these rules pass you by at what seems like the speed of light, what you want to see is why they seem to be true, and then you want to practice them. I'm going to now give you some examples that will illustrate some of this, but this won't make up for your own efforts a little bit later. Here's the example. Again, the object here is simplify, so we can use some of these rules. Let's start off with a couple of easy things. 8 to the 2/3 power. Well, that's complicated looking. Let's see if I can simplify it and make it a little easier to work with. If I rewrite this as 8 to the 1/3 power squared, of course that's the same thing as the original, 2/3, this is 2 times 1/3. I notice something now I didn't notice before. I know from my experience that 8 is the cube of 2. So the cube root of 8 is 2. So now I have 2 inside squared. Well, that's easy. That's 4. So what looked like a difficult number to begin with, 8 to the 2/3, is really just a very familiar number, 4. Let's do some more like this. How about 16 to the 3/2? Now again, I've chosen this so that things will work out in my favor. If I rewrite this as 16 to the 1/2 cubed, I now recognize that 16 is a perfect square, so I can take the square root and get 4 cubed. And 4 cubed is another number that's not too unfamiliar, 64. All right, well those were particularly nice. Let me do one that is not nice. Suppose I have an expression like minus 8 times x to the 5th all to the 1/3 power. Now let's see if I can simplify this a little bit. First of all, I'm going to run the 1/3 over each of the factors as the rule says I can do. Minus 8 to the 1/3 times x to the 5th to the 1/3. And I will continue my equal signs down here. Where can I go from here? Well, really not too much farther. I might recognize that minus 8 has a cube root 1/3, which is minus 2. So I can write minus 2 here times x to the, well, there's nothing I can do with this. X to the 5th to the 1/3, I could write it as x to the 5/3 if I like. That's a perfectly good way of stopping. Some people prefer, however, that you take it one step further and write minus 2, and then realize that the x to the 5/3 can be rewritten as x to the 3/3 times x to the 2/3. Remember how this works? If you have two bases that are the same, you add the powers. If you can see my little 2 here, 2/3 and 3/3, of course, add back to 5/3. The advantage to this is you now have minus 2, x to the 3/3 is x, and then times x to the 2/3. Now, I only gave you both of those because there's different taste in the world. I prefer, frankly, the first one, where only a single power of x occurs. And it's an improper fraction as the rational exponent, but that doesn't bother me. So there's a series of a few examples. Let's look at some more that involve more variables so that we get some experience here. Example, another one that's simplify. And here is the original. X to the 5th y under the square root symbol all over x cubed y cubed under the square root symbol. Now I'd like to simplify that. My first instinct is to get rid of the square roots. But actually it pays to leave them there for just a moment and to realize the square root on the top and the square root of the bottom, this can all be written as the square root of the entire fraction. X to the 5th y, x cubed, y cubed. Now we can rewrite that square root as 1/2 power. And we can also notice inside that things are going to work out nicely. If I have x to the 5th on the top and x cubed on the bottom, that leaves me with x squared on the top. Remember, it's 5 minus the 3. Here I have y over y cubed. I can take y here and cancel it, or write y over y to get 1, and be left with y squared on the bottom. I can reinterpret the inside as x over y quantity squared, all taken to the 1/2 power. Now this is all even powers, which means in taking a root like this, as the rule said, we had a theorem earlier that said, what I should end up with is the absolute value of xy. Because the inside square would remove any negative numbers that appeared in here, and then the square root would not recover them. So I don't know what's inside. The best I can do is write down x over y absolute value. Now, look at that. That's much simpler than the original one. That, after all, is the point. All right. Let me do one more that is more complicated than any of the ones we've seen before I come back and give you a list of tips. So this is a longer exercise. And this is big. So let's write this down. Square root of 1 plus x minus x times 1 over 2 square root of 1 plus x. And all of that is over 1 plus x. All right? And we will also assume here, I'll put it over here, we will assume that x is greater than or equal to 0. That way, if any absolute values turn up, the absolute value of a number that's 0 or bigger is just itself, and I won't have to worry about that. All right, here's my first piece of advice. This is a big fraction. Here's a hint. Rewrite it this way. 1 over 1 plus x. There's the denominator. Think of it as a fraction 1 over that times the large part of the top. So I'll just copy the top, square root of 1 plus x, minus, and this x here can be written on the top of this fraction, so I'm going to do that. X over 2 square root of 1 plus x. Now see, I've already made some simplifications that make life easier for me. The x here I have moved up to the top. That's what appears here. And I've rewritten this so that I have 1 over this out front. Now you see how this works? This numerator, if I multiplied it back out, would multiply times 1, and I'd get the fraction back. But now it's out of my way temporarily, and I can just concentrate on this. Well, what I need to do here is to add this into a single fraction. The problem is the first one has no denominator. So the second denominator is the one I'm going to be looking for. How will I get that? Well, the best idea is to multiply the first thing here. Remember, we can think of this as square root of 1 plus x over 1. Multiply top and bottom here by the same thing so that I don't change the problem. The same thing being this number here. So what I will do is put into here, right there, I will multiply 2 square root of 1 plus x over 2 square root of 1 plus x. Now that's 1, so that won't change the problem, but it will give this the proper denominator. So let me continue on to another page. I'll bring this one back so you'll see what I've just done. But now I have, repeating this, 1 over 1 plus x, that doesn't change. But now inside here, all of this has the same denominator, 2 square root of 1 plus x. That's by design. On the right, I have minus x, that's what was there before. And on the right, I have 2 times the square root of 1 plus x squared. Now let me bring the previous sheet back so you can follow this. The front 1 over 1 plus x has not changed. In here, I've multiplied top and bottom of the first fraction by these numbers. The bottom makes the denominator the same as this, so I can add the fractions. On the top, I'm left with 2 times this times this. 2 times square root of 1 plus x squared. On the right, I have a minus x. So remembering that, see what I have here? 2 square root of 1 plus x squared minus x. Okay, now let's continue. Notice with this single fraction on the left and the right, I can multiply the two denominators, and I can multiply the two numerators. That's how you multiply fractions. So I'm going to get one large fraction. On the bottom, I'll have 2. And what happens when I multiply 1 plus x times the square root of 1 plus x? Well, think about that for a moment. 1 plus x is 1 plus x to the 1 power. Square root of 1 plus x is 1 plus x to the 1/2 power. So when I multiply this by that, I end up with 1 plus x to the 1 plus 1/2 power, which is 3/2. Now what happens on the top here? 2 stays. Square root of 1 plus x squared, by its very definition, is going to be 1 plus x. Now there's a place where I might have needed absolute value if I hadn't chosen my x to be positive to begin with. Minus x. Well, the top can be simplified. This is 2. And then 2x minus x gives me plus x. On the bottom I have 2 times 1 plus x to the 3/2. And that's where I am going to stop. There's no other cancellation that seems apparent to me, so I'll just leave it like that. And this is much simpler than, let's bring the original back. Oh, that is the original. The original is this large fraction to begin with, and I have now simplified it into this. Now the more work that you do, the more you will appreciate these kinds of operations. Okay, let me go back and now start giving you some more advice and end up with a few tips on working with rational expressions. Here's a note that I'm going to make, because this is something that people get upset about, and I think we can make this perfectly simple. And I'll do it with an example so you see what I mean. I will write down 1 over square root of 2. Now, that is a perfectly good fraction. And it's simple. 1 square root of 2. Not very hard. But, however, some people, and I am not one of them, some people prefer we write the following. Instead of the nice, simple, elegant 1 over square root of 2, they want you to remove square roots from the denominator. Multiplying the top and bottom by square root of 2 will do that, because the top will be square root of 2 and the bottom, square root of 2 times itself, of course, is 2. They prefer this form on the left. I prefer the simpler form. This technique is called rationalizing the denominator. Rationalizing, I can spell it correctly here, rationalizing the denominator. This is not crucial. This is not overly important. Why was this invented in the first place? Because calculations like this used to be done by hand. And when you do things by hand, it does help to have a rational number or just an integer in the denominator. However, with the advent of calculators and computer algebra systems, this number up here, which is more elegant and simple, is just as easy to work with as this one. So, although this is a technique that exists, I'm not going to stress it, and you shouldn't worry too much about it. All right. Well, we've had a lot of notation now, and before I leave you, I want to first do a notation summary, just so you are clear on what these notations mean and don't mean. The first one, of course, I'll remind you that x to the 0 equals 1 as long as x is not 0. Well, since we've raised the question of 0, what about 0? Well, let me give you all the properties of 0 that we've uncovered in this section, plus a few others from before. And let me take a particular number to do it. 5 times 0, as you know, is 0. 0 over 5, as you know, is 0. 0 to the 5th, I hope, as you know, is 0. What about 0 to the minus 5 power? I'm going to put that in quotes because that's undefined. Why is it undefined? Because the minus in the exponent means this is 1 over 0 to the 5th, and you can't divide by 0. What is 0 to the 1/5? It is 0. What is 0 to the 0? Again, this is undefined, as we indicated earlier. So there are all your basic 0 facts. So you might say that we've just discussed nothing. All right, continuing the notation for numbers that are not 0, here's what you can say, just to get this all clear in your mind. Okay, 5 times x means what? It means x plus x plus x plus x plus x, right? You add x 5 times. X over 5 is the same as 1/5 times x. And notice, be very clear, this is not the same as 1 over 5x. Again, it's a matter of grouping. This is 1/5 times x. This is not. See, this is 1/5 times 1 over x. And so these are definitely not the same thing. Then there's x to the 5th. Now what was that? That's x times x times x times x times x. So it's the product of 5 x's. What was x to the minus 5th? This is not negation. It is not subtraction. It says write x to the 5th on the bottom. And finally, what is x to the 1/5? Well, that is by definition the 5th root of x. That's the number you multiply by itself 5 times to get x. Now some tips, and then you'll have a chance to practice on your own. Tips. You'll want to jot these down. Always, another one of my always remarks, always rewrite square root or the nth root of a as a to the 1 over n. First. Do that first and then proceed with whatever problem you're working on. Okay? Return to this form, this radical form, only if it is requested of you. Otherwise, leave things in the rational form. Box to 1 over n is much easier to work with. So that's a piece of advice from my experience. And then finally, remember that one case that we have difficulty with, when you have an even root of a negative number. Okay? Even root of a negative number is not real. In fact, it's what's called a complex number, and we will talk about that again. But for now, we've had a lot of information about nth roots and rational exponents, and I think it's time for you to take a little time of your own and practice these.